Capnography is the monitoring of end-tidal carbon dioxide levels, or EtCO2. A capnogram measures EtCO2 levels as the partial pressure of CO2 in an expiration in units of millimeter per mercury. Normal CO2 levels in an expiration ranges from 35 to 45 millimeters of mercury. Capnograms are helpful and easy to use since normal readings for quantity, shape, and trends of the waveform are the same for men and women of all ages. Furthermore, deviations in capnography waveform can be used to diagnose a large variety of respiratory arrhythmias and other medical conditions, such as shock, hypoxia due to asthma, hypoxia due to medical obstruction, emphysema, and heart failure. Capnography has also become integral to monitoring the effects of anesthesia during procedures. The partial pressure of CO2 in the body controls the rate of respiration, which in turn determines the amount of oxygen being supplied to the body and the rate of removal of metabolic waste products at any moment. PCO2 levels regulate many processes in the body, including blood pH, breathing, and affinity of hemoglobin to oxygen. For example, when PCO2 levels are high, the rate of respiration increases to reduce it. If PCO2 levels remain high, the patient will experience a drop in blood pH, leading to a condition called respiratory acidosis. Respiratory arrhythmias occur because the body's chemoreceptors are unable to detect changes in PCO2 levels or are unable to elicit a respiratory response to correct it. Over the years, capnography has developed into a rapid and accurate way to measure PCO2 levels in a variety of different settings and procedures. Capnography was first used in World War II to measure the levels of CO2 soldiers were being exposed to. It was used for the first time in a medical setting in 1950 to monitor CO2 levels of patients when placed under anesthesia. However, with the advent of smaller devices, it was not until the 1980s that capnography was regularly used in practice. There are two main types of capnography, mainstream and sidestream. In mainstream capnography, the CO2 sensing apparatus is inserted directly into the patient's airway through an endotracheal tube. Direct insertion allows for instantaneous and unobstructed monitoring of CO2 levels, but the apparatus must be heated above body temperature to avoid false readings due to condensation in breaths. In sidestream capnography, a thinner sampling tube is inserted into the patient's airway. This sampling tube is connected to an external adapter which measures PCO2 levels in the expirations of the patient. While sidestream capnography may be more comfortable for the patient due to the thinner tube, readings are not as accurate due to a possible phase shift in waveform due to difference in time between expiration and sensing of CO2 levels. Furthermore, newer sidestream devices that have its sensor in a nasal cannula can accurately determine PCO2 levels without requiring the patient to be intubated. A capnogram is obtained through infrared absorption spectroscopy. Since CO2 is a gas that contains two dissimilar atoms, it is able to absorb infrared light with a wavelength of 4.3 micrometers. To measure PCO2 levels in a sample, a photodiode in the apparatus emits a constant amount of light with a wavelength of 4.3 micrometers. An IR photodetector measures the absorbance of light that passed through a sample of expired respiratory gases. Then, the amount of light absorbed by the photodetector is compared to the constant amount of light being emitted by the photodiode to quantify the PCO2 levels in the breath. The data generated by the photodetector is outputted to a capnograph. The sampling rate for our device was set at 6 Hz. This was done because at a maximum breathing rate of 45 breaths per minute, the frequency is 0.75 Hz. Using the Nyquist sampling theory, the sampling frequency rate should be double the frequency of expected signal to prevent any data loss, which is 1.5 Hz. Furthermore, since the waveform of PCO2 requires 4 points to make a complete data set, a sampling rate of 6 Hz should be used to capture all of the points needed to allow for accurate data analysis of PCO2.
Our circuit is comprised of 4 stages including a photodiode with a current to voltage converter, transimpedance amplifier, high-pass filter, and low-pass filter. Each stage plays a definitive role in signal acquisition and processing. In the device, an IR source constantly emits infrared light. The number of incident photons that are detected by the photodiode on the opposite end generate a proportional current. The current to voltage converter then transforms the current into a voltage signal. The voltage signal is amplified with the transimpedance amplifier. This type of amplifier was selected because it presents a low impedance to the photodiode and isolates the output voltage of the op-amp. Using resistor values of 1 megaohm and 1 ohm, a gain of 10 to the 6 is generated. This was used because the voltage prior to amplification is often in microvoltages. The signal then passes a high-pass filter. The high-pass filter removes low-frequency signals including noise and DC offsets. Because electrical components can deviate from their expected values, the high-pass filter is important in removing some noise and generating a steady baseline. The estimated slow breathing of an adult would be 2.2 Hz, so a cutoff frequency of 0.5 Hz was designed using C1 equals 72 millifarad and R4 and R5 equaling 1 ohm. R4 and R5 had the same resistor values to prevent further amplification. In the low-pass filter stage, extraneous noise is removed. Because a rapid breathing adult signal would reside near 6 Hz, a cutoff frequency twice as large, 12 Hz, was selected. This was done by setting C2 equals 1 megafarad and R6 and R7 equal 15 ohms. Once again, R6 and R7 have the same values to prevent further amplification. Although using these values do not return an exact cutoff frequency of 12, they are selected based on market availability and economic efficiency. With the signal passing through the low-pass filter, short-term fluctuations are removed and long-term trends are preserved. The angle between phase 2 and phase 3 is called the alpha angle and can be used to assess how well air is being ventilated out of the lung. A normal alpha angle is 100 to 110, and values larger than that can indicate an obstruction in the patient's airway. Phase 3 is the expiratory plateau. The partial pressure CO2 level is maintained at a slightly increasing rate. This is where the peak end tidal CO2 level will be observed. Furthermore, the last alveolar gas will be sampled in this phase, as inspiration will soon follow. The angle between phase 3 and phase 4 is called the beta angle and can be used to measure how well rebreathing occurs. Rebreathing is indicated by a beta angle larger than 90 degrees. Lastly, phase 4 is the expiratory downstroke, and this is where inspiration begins.